Hello students, let us learn today about eclipses in this video and about light's direction, then about the pinhole camera.
Has it ever happened to you that while watching a movie in the theatre, your view was suddenly blocked by the head of the tall man in the front seat? Have you ever wondered how a small head can obstruct your view of a 70 feet wide screen? This is very similar to a phenomenon in nature. Did you know that during solar eclipse, the small moon can sometimes completely block out our view of the largest star, the sun? Let's find out how. We know that the moon revolves around the earth. Sometimes, on its journey around the earth, the moon comes between the earth and sun. When the sun, the moon and the earth are in a straight line, with the moon between the sun and the earth, it blocks the view of the sun from the earth. The moon's shadow then falls on the earth's surface. This phenomenon is called a solar eclipse. A solar eclipse only happens during the new moon phase. Since the moon is smaller in size than the earth, the shadow it casts covers just a part of the earth. The moon's shadow falls on the earth in two ways. One part is the full shadow of the moon, also known as the umbra. It falls on a very small area of the earth. When viewed from this area on the earth, the sun looks completely blocked out or dark. The other part of the shadow of the moon is the faint outer shadow, also known as the penumbra. This shadow covers a larger area of the earth. When seen from this area on the earth, the sun looks partially blocked out or partly dark, while a brighter part of the sun still remains visible. Since the moon is relatively small, its shadow does not fall on the whole earth. So what happens to those places that do not come under the moon's shadow? Well, they do not experience any eclipse at all. Depending on the part of the sun visible from the earth, solar eclipses are of four types. During total solar eclipse, the moon almost covers the whole view of the sun from certain places on the earth. This is when the moon is at its perigee or closest to the earth in its orbit. Although it is daytime, all that we can see is a large black disk where the sun was, with only the sun's bright atmosphere or corona visible to us. During annular solar eclipse, the moon blocks almost the whole view of the sun from Earth. In this stage, the sun looks like a very bright golden ring. At this time, the moon is on its apogee position, that is, farthest from the Earth. During the annular solar eclipse, only the bright rim of the sun is visible to us as a golden ring. A hybrid solar eclipse is a combination of both the total and annular solar eclipse. In this type of eclipse, some parts of the earth experience a total eclipse, while other parts see an annular eclipse. Hybrid solar eclipses are quite rare. Partial solar eclipse is visible from the areas of the earth where the moon casts its penumbra shadow. During partial solar eclipse, only a part of the sun is hidden by the moon. Thus we see only a slice or half of the sun blackened out, depending on where we are viewing it from the Earth's surface. You may be wondering how the moon blocks the sun, which is 400 times larger than itself. Well, that's because the moon might be small, but it is almost 400 times nearer to the Earth than the sun. In effect, because of its proximity to Earth, the comparatively small moon can triumphantly block out even the largest star from our view from time to time. The moon takes almost a month to complete a cycle around the Earth. To be more specific, the moon orbits the Earth in 29.5 days. When viewed from the Earth, we get to see different portions of the moon's illuminated side. On a full moon night, the Earth is in between the sun and the moon. On such occasions, the sun, the Earth, and the moon are at times in a straight line. This is when the moon passes behind the Earth, so that the Earth blocks the sun rays from striking the moon. This phenomenon is called lunar eclipse. The shadow the Earth casts has two parts. The dark inner shadow of the Earth is referred to as umbra, while the light outer shadow of the Earth is referred to as penumbra. The shadows cast by the Earth on the moon's surface determine the type of lunar eclipse that will occur. When the entire moon passes through the Earth's dark inner shadow, or the umbra, we get a total lunar eclipse. A total lunar eclipse is quite spectacular to watch. No direct sunlight reaches the moon at this stage, as the sun's direct rays are completely blocked out by the Earth's shadow. As it goes through the dark inner shadow, or umbra, the full moon changes color from a pale yellow to different shades of copper, and finally back to a pale yellow shade, as it completely exits the Earth's shadow. Why does this happen? In this stage, some of the sun's light still manages to reach the moon, as the rays get refracted by the Earth's atmosphere. The air and dust in the atmosphere absorbs most of the blue light and lets only the red light pass through. This red light causes the moon to turn a copper red color. When only a part of the moon passes through the umbral shadow of the Earth, we get a partial lunar eclipse. During this phase, the moon does not get fully blocked by the Earth's shadow. When the moon passes through the light outer shadow of the Earth, or the penumbra, we get a penumbral lunar eclipse. This type of eclipse is difficult to observe, as the moon does not get totally shadowed. Only the intensity of light falling on it gets reduced. A rare kind of eclipse is the total penumbral eclipse, wherein the parts of the moon that are closer to the umbral shadow enter into complete darkness. We view a full moon once every month. Then why is it that we do not get a lunar eclipse every month? Well, that is because the moon's orbit around the Earth and the Earth's orbit around the Sun do not lie on the same plane. The moon's orbit is tilted at an angle of 5 degrees. So, the Sun, Moon and Earth do not fall in a straight line every month. We see a lunar eclipse only when they do. Do catch a glimpse of the lunar eclipse the next time you get an opportunity. And remember that it is nothing but the shadow of our own planet that is covering the moon.
You must have seen a spotlight on a stage or a beam of flashlight in the darkness. So what's common between all light beams? Aren't they all straight? Let's do a small experiment to find out more about the path of light. You will need a light source for this experiment. Let's use this beautiful candle. Now take 3 cardboards of the same size with a pinhole made in the center of all the cardboards. Now place these cardboards in a straight line in front of the candle and look at the candle from the other side of the cardboards. I am sure you are able to see the light coming from the candle, right? Now, what if we move any of the cardboards and see if we can still see the light from the candle? Why don't you see the light now? You are not able to see the light through the pinholes because light travels in a straight line. And when you displace one of the cardboards, light gets blocked and cannot reach your eye.
Our primary source of light comes from the sun. Other sources of light include flames from fire, the filaments in light bulbs, and the gases in fluorescent tubes. Light originates from excited electrons in atoms. When an electron becomes excited, it will move to a higher orbit. Eventually, it will return to its original orbit, emitting light in the process. Light travels in the form of transverse waves and is a small part of the electromagnetic radiation that is emitted by luminous objects. A transverse wave indicates that the molecules are moving in a vertical direction, meaning they are moving up and down, a direction that's perpendicular to the movement of the wave. For a visual representation, we only need a piece of rope that is several feet long. With one end tied to a doorknob, we can gently shake the opposite end up and down. In this case, the vibration moving along the rope will move forward as a transverse wave. Their shape will look like a series of hills and valleys. The hill or highest point is the crest. The valley or lowest point is the trough. The distance between one crest to the next, or from one trough to the next, is the wavelength for that particular wave. Now let's go back to the electromagnetic radiation. On one end of the radiation spectrum are the radio waves, which have longer wavelengths, and on the other end are gamma rays, which have very short wavelengths. Visible light is a very narrow band within the large electromagnetic spectrum, from about 400 nanometers for violet light to about 700 nanometers for red light. Visible light is made up of only 7 colors: violet, indigo, blue, green, yellow, orange, and red. The waves adjacent to the red color are infrared, and the waves adjacent to the violet are ultraviolet. The speed of light in a vacuum is exactly 299,792,458 meters per second, or about 300,000 kilometers per second, or about 186,282 miles per second. Summary: light is an electromagnetic wave. Light moves in the form of transverse waves. Visible light is composed of 7 colors. Light travels at a speed of 300,000 kilometers per second.
Pinhole camera. A pinhole camera is a simple camera without a lens. Instead of the lens, it has a small opening, a pinhole, to allow light. The principle behind the pinhole camera is very simple. Light passes in a straight line through the pinhole and creates an inverted image on the screen. To understand how a pinhole camera works, we'll build one. We'll need a deep cardboard box, a sharp pin, duct tape, and a sheet of tracing or waxed paper. Begin by checking the sides and bottom of the cardboard box. Ensure that there are no holes or gaps through which light could enter. Using a thick, sharp pin, pierce the center of the box bottom. Next, use the duct tape to tightly secure the waxed paper or sheet of tracing paper completely across the open end. This will act as a screen. Hold the pinhole camera so that the pinhole is pointed away from you and the paper is facing you. Point the camera outside a window at a bright object such as a tree. You should be able to see an upside-down image of the scenery projected onto the paper screen. Let's see how the image was formed. The light rays reflected off the distant object travel in a straight line, converging at the pinhole. Through the hole, the lines will continue to travel in a straight line path and strike the screen. As a result of the intersection of straight lines, the image on the screen will appear inverted. This is referred to as real image because it can be captured on a screen. Summary: a pinhole camera is a simple camera without a lens. The pinhole camera works on the principle of light traveling in straight lines. Pinhole cameras produce an inverted, smaller image on a screen.
Image formation in plane mirrors. A mirror is a polished surface that reflects light waves. A plane mirror is flat, like a geometric plane. When a ray of light strikes a plane mirror, the direction is changed so that the ray passes back in the direction from which it originated. If we draw an imaginary line, referred to as the normal, which runs perpendicular to the plane mirror, the angle created between the incoming ray and the normal will be the angle of incidence. The angle created between the reflected ray and the normal is the angle of reflection. The law of reflection states that the angle of incidence will be equal to the angle of reflection. When we tilt the mirror at an angle theta, the reflected ray will rotate through an angle of 2 theta. If we place a lighted candle in front of a mirror at a distance of x, we will see an image of the candle at a distance of x, seemingly behind the mirror. Image is virtual, will be upright, and cannot be captured on screen. Let's look at the mechanism of the image formation. The rays from the candle will strike the mirror's surface at different angles and be reflected. If we projected the reflected rays behind the mirror, they would converge at a point, forming a virtual image. The distance between the virtual image and the mirror will be the same as that of the distance between the object and the mirror. Although it is upright, an image in the plane mirror will be laterally inverted. To check this, let's hold the word ambulance in front of a mirror. The word will appear reversed. It is for this reason the word is reversed when painted on the front of emergency vehicles. It can be read correctly in the rear view mirror. A plane mirror will produce an image that is virtual, upright, and the same size as the original object. It will also appear at the same distance as the object is from the mirror, but it will be laterally inverted. Summary: a mirror is a polished surface that reflects light waves. A plane mirror is flat, like a geometric plane. A plane mirror will produce an image that is virtual, upright, and the same size as the original object. It will also appear at the same distance as the object is from the mirror, but it will be laterally inverted.